Now that we have our basic application structure in place, let's add database support to our Quart application. We'll be using PostgreSQL as our database, and we'll set up a complete database migration workflow using Alembic. This is a crucial part of any production application as it allows us to version control our database schema changes. Let's start by adding the required packages to our Poetry environment. Open up the PyProject TOML file and add the following dependencies. Let's understand what each package does. The CyclePG2 binary package is the PostgreSQL adapter for Python. It's what allows our Python code to talk to PostgreSQL. The databases package with the async.pg extra provides async database support, which is crucial for our Quart application. SQL Alchemy is our ORM, Object Relational Mapper, that allows us to work with databases using Python objects instead of raw SQL. Finally, Alembic is SQL Alchemy's database migration tool, which helps us manage database schema changes over time. Save the file. Now let's rebuild our web container to include these new packages. Let's set up our database connection management. Create a new file in the My App folder called db.py. This file does several important things. First, it creates a metadata object that will store the schema information for all our models. Then it provides an async function that creates and returns a database connection pool. Notice we're using connection pooling with min size equals 5 and max size equals 20. This is a performance optimization that keeps a set of connections ready for use. Save the file. Before we create our counter model, let's set up the counter structure. Create a new directory called counter app inside my app and add an empty init.py file to make it a Python package. Now let's create our counter model. This will be a simple table with just an ID and a count field. Create a new file called models.py inside the counter app folder. In this model, we're using SQL Alchemy Core instead of the ORM. Why? Because when working with async applications, the Core API provides better performance and is more straightforward to use with async drivers. We define a table named counter with 2 columns, an auto-incrementing ID, and a count field that will store our counter value. Save the file. With our model in place, let's set up Alembic for database migrations. First, we'll initialize Alembic in our project. This command creates a migrations directory and an Alembic ini file. Let's configure Alembic by updating this file. Find the SQL Alchemy URL line and update it to use our configuration. We're using variable interpolation here to make our configuration environment agnostic. These variables will be populated from our settings. Save the file. Now we need to add a few lines to the migration's env.py to connect our models to Alembic. First, we'll add these imports at the top of the file. Then, near line 25, we'll set our metadata. Finally, we'll add the configuration section that will allow Alembic to read our environment variables. Save the file. Now let's generate our first migration. When we run the following command, Alembic will compare our models against the current state of the database and generate the necessary SQL to synchronize them. This will create a new file in the migrations/versions directory. Let's look at what Alembic generated. Alembic migrations are like version control for your database schema. Each migration file has a unique revision ID and contains two main functions. Upgrade. This function contains the changes needed to move your database forward to this version. In our case, it's creating the counter table with its columns. Downgrade. This contains the reverse operations needed to undo this migration. Here, it would drop the counter table. Think of these migrations as a chain. Each migration knows about the one that came before it through the down revision variable. Alembic uses this to know how to move forward and backward through your database changes. Now let's apply this migration. The upgrade head command tells Alembic to apply all pending migrations in the database until it reaches the most recent version. Let's verify the tables were created in our database. We can connect to PostgreSQL running in our Docker container. This command breaks down as docker compose exec db, run a command in the running database container, psql, the PostgreSQL command line interface, -u app user, connect as our application user, app, connect to the app database. Once connected, let's see what tables were created. You can see two tables, our counter table and an Alembic version table. The Alembic version table is special. It's how Alembic keeps track of which migrations have been applied. Let's look at its contents. This single row contains the ID of our last applied migration. Alembic uses this to know where in the migration chain we currently are, which helps it determine what migrations need to be applied when we run upgrade or what migrations need to be reverted when we run downgrade. Exit the PostgreSQL prompt by typing \q and pressing enter. Now that we've verified our database is properly set up, we can move on to starting our application. Let's create our counter blueprint and views. Create views.py inside the counter app folder. First, we import what we need. Blueprint from Quart for creating our modular component. Current app, which gives us access to the application context, including our database connection, and our counter table model that we created earlier. We create a blueprint named counter app. This is what will register in our main application later. Here, we define our root route and make it async since we'll be doing database operations. We will get our database connection from the application context. The type ignore comment is for MyPy. We'll talk about linting in the next module. Create a select query using SQL Alchemy Core's expressive syntax. Fetch all rows that match our query. We expect either 0 or 1. And initialize our count variable. Now comes the interesting part, handling the two possible scenarios. If we don't have any results, not len result, this is our first visit ever. We need to create an insert statement, setting count to 1, execute the insert statement, explicitly commit our transaction, and set our local count variable to 1. If we do have results, we're incrementing an existing counter. Get the first and only row. Calculate the new count by adding 1. Build an update statement that updates our counter table, matches the row by ID using countertable.c.id to reference the column, sets the count to our new value, and finally execute the update and commit the transaction. Finally, we return a simple HTML response showing the current count. Notice how we use await for all database operations. This is crucial because these operations take time to complete. While we're waiting for the database, other requests can be processed. When the database operation finishes, we resume exactly where we left off. Also notice our transaction management. We explicitly commit after both insert and update operations. In a more complex application, we might want to use a context manager for transactions. But for this simple example, explicit commits work fine. Save the file. For our last step, let's update our application.py to include our new counter blueprint and database connection management. First, we'll import the new counter app blueprint and the DB connection from the new DB module. And then in line 27, we do the following. We've added the counter blueprint registration and, most importantly, two special lifecycle hooks using before serving and after serving decorators. These decorators are specific to Quart and are crucial for proper application lifecycle management. The before serving decorator runs before the first request is handled by our application. This is different from Flask's before first request in an important way. In an async application, we might have multiple workers handling requests, and we need our database connection to be available to all of them. By setting up the connection in before serving, we ensure that our database connection pool is established once when the application starts, not when the first request comes in. Similarly, after serving runs when we're shutting down our application. This gives us a chance to properly close our database connections. This is crucial for preventing connection leaks and ensuring all our database operations are properly completed before shutdown. Both of these hooks are asynchronous because database operations in our application are asynchronous. We store the database connection in app.dbc, which makes it available throughout our application via the current app proxy. This is a pattern that ensures we're reusing connections efficiently rather than creating new connections for each request. Save the file. With everything in place, we can start our application using Docker Compose to bring up both our web service and the PostgreSQL database. You might see quite a bit of output as both services start up. This is normal. Once you see the message that the application is running, visit HTTP localhost 5001 in your browser and you should see the counter starting at 1. Refresh the page and watch it increment.